Welcome to the classroom. Today we're going to be teaching with an augmented reality sandbox. What is an augmented reality sandbox? Well, that is a box of sand that we can play with, and we can create a topography. So we can build up a mountain here. As we raise up the ground surface, the contours of the topography are automatically projected with the projector here. So we're detecting the height and then projecting that. And we're also using color, so we can see the reds are higher and the greens are lower. We even have water there, and if we dig a hole, we can extend the lake and we can create a river channel, okay, that's going around this mountain and connects over here. So we can do all kinds of things. We can even make it rain, and we can make volcanoes happen. Pretty awesome. But what can we use it for to teach about structural geology? That's what I want to try to use, because I've struggled in the class to try to teach it on paper, and then also trying to teach it remotely during the pandemic. So what we have here is the sandbox, and I'm hoping that's really going to help students understand the three-point problem. What is the three-point problem? Remember, if you watch the shorts, we can understand the orientation of a plane in space simply by knowing 3 points on that plane. And in geology, we have lots of planar structures. So we can use any of those planar structures and understand spatially in our topography where it exists. So right here, I've got a shale sandstone contact, okay? And it exists at the 900-meter topography elevation, okay? So it's 900 meters above sea level. If we pretend that these contour levels represent 20-meter increments, so the next one down is 880 meters, the next one down 860, and so on, or up, that tells us the elevation of the hill, okay, that we're dealing with. Now, the other observation that we would make as a geologist, we could measure the contact, the orientation, the strike, and the dip, all right? So if we have a strike, that's using the right-hand rule. My thumb points in the strike direction, and my fingers are in the down-dip direction. Then we can measure that at this location, and we can project that spatially. So we know at the 900-meter elevation contour, all right, this contour comes around over here. If we know the strike is in this direction, then this contact must exist at the same elevation, all right? Because it's a strike line. The strike line is a horizontal line on that plane, all right? So let me draw that here, okay? And it's orientated like this. Strike line is like that, all right? That is the horizontal line on the plane. So that's a key thing to remember. All right. So I've got some popsicle sticks here that I'll use as our lines. All right. So we know that this is at 900 meters and the strike is in the orientation of that popsicle stick. Okay. We can see our popsicle stick come out over on that side over here. All right. And let's see, is that the 900 meter? Look, it's the 900 meter elevation contour. That's a contact between our sandstone and our shale, okay? That popsicle stick went straight through on a horizontal line and popped out at the same elevation as those 2 points. Now, that gives us our strike orientation, but where does it exist down dip, okay? Remember my finger's pointing down dip? So if we know our dip is at a 36-degree angle, all right, in reality, if we're out in the field, we cannot project popsicle sticks through the ground, okay? We have the luxury here for teaching. So we need to actually calculate where we might expect that outcrop to exist. We can calculate what elevation it is, and then we can go down, walk down the hill, and look for it, okay? Because we want to make as many observations as possible. Pretend we're going to construct a road through this hill. We want to know where the sandstone exists and where the shale exists, because that can tell us about the amount of materials we need to excavate, what kinds of materials, what kinds of problems we may encounter. The sandstone is strong and hard, the shale when it's exposed to water, it becomes weak and weathers easily. So we need to know these things when we are constructing roads, for example, or pits and various infrastructure. So if we take our popsicle stick and we project it in space down the dip direction, it will be perpendicular to the strike orientation, okay? But we don't know where it exists down there, but we can calculate it, all right? So if we know that we are going to go, say, down to the next contour line, okay? This is 900, so we're gonna go down to the 880 position, okay? So we know somewhere down here, we have a contact, okay? And it's 20 meters down, all right? And we have a horizontal line in space, okay, that we know exists, all right? That represents a triangle. So we have our down dip length, okay? We know it's 20 meters down at some place on the 880 meter elevation contour. The thing we don't know is that horizontal distance. So we can calculate that. Let me draw it over here, okay? So we have a point in space, 900 meters, okay? Somewhere over here, we have a point in space that's directly above the contact at 880 meters, okay? And so we know this angle, okay, we'll call it 36 degrees. We're trying to figure out this horizontal distance, and then we can use that and plot it on our map, okay? So we know we've gone down 20 meters, all right? And just using trig, we can figure out with the angle and the drop where horizontally we exist. There we go. Where we exist on the map, all right? So pretend we know where that is, then from this observation point, okay, we can project our location in the dipping direction to that place, okay? And if it exists there, then we have solved our 3-point problem by knowing, and we can plot our contact then between our shale and our sandstone at that location, all right? And we can repeat the problem for different places on the map. So if we want to go down to 860 and so on, we could just repeat that and figure out where that contact exists spatially throughout the entire map. And I'm just, doing that offhanded, but now we can trace out that contact. And in reality, we can go and walk there. We can take more measurements, more observations if we see that contact in space. So it's really handy when you're out in the field in a great big mountainous region to understand where you've got to go to find more information, because that is a tricky thing to do out in nature. Thanks for watching, and we'll do a more complex problem in the future. So don't forget to like and subscribe and continue to watch the videos.